His work focuses on how to bring real movie-making techniques into the virtual world, such as camera movement and shot composition. He builds small tools that can help and control virtual cameras to make the pieces look more impressive and expressive. He has published many research papers, has several patents, and also worked with industries such as utility and Technicolor to apply his research in real world projects. So today he will share his experience and ideas on how virtual cameras and cinematography can change the way we tell stories in an interactive and immersive media. So please join me in giving him a warm welcome.
Thanks a lot. It's my pleasure to be here today. I would like to warmly thank you, Lucien, for the invitation, and also the other professors from the department. And of course, we'll welcome all to this presentation. Okay, so quickly we're going to talk about cinematography, and more specifically computational cinematography. So cinematography is the art of making movies, and we're going to try to see how we can sort of insert some computational techniques in this topic. So just some elements of context. I'm coming from France, and I'm coming from Brittany, more precisely, so the red region over there. So it's a seaside region. I'm leading a master's on computer engineering, and I'm a member of a research lab, which is quite large. It's one of the oldest research labs in France. It's 600 researchers on all topics related to computer science and robotics. I'm also a member of a specific research team, which is called Virtus. And Virtus, we're looking at 3D animation, character animation, but also crowd simulation. When you have a crowd of people and you want to simulate them in 3D environments. And of course, cinematography. So I just took a few shots of my area, so it's quite close to the sea with a very nice landscapes, with very old wooden houses and some pancakes. So very similar to some of the pancakes you get here, and then you will put whatever you like in the middle of the pancakes. So it's really good, and if you want to come and visit, please send me an email. I'll be happy to host you. Okay, so cinematography is an art. Okay, we all know that. It's one of the 7 arts, and it's an art which is constrained by a number of techniques. You can't think of an art without thinking of the underlying techniques you need to build an art. It's a technique because you need a device, which is a camera. You need some lights, you need some characters, you need to stage the characters in the scene so that you can build a story. And this art is something which relies on the staging process. So staging is where you would place the characters, where you would place the cameras, and where you would place the lights. So you can see in this sequence the work which is being done in how you would frame the people in the environment and how the light is changing the atmosphere of the environment. It's also about the orchestration. The orchestration is how everything is moving together. The people are moving, the camera is moving, well, not in this sequence but in some other sequence. Everything is moving together. And it's also about how the shots are going to be cut together. You've got a first shot, you cut to a second shot, you cut to a third shot, and this is the editing process. So cinematography is about all these components that you would put together. And there are millions and millions of possibilities of combining lights, cameras, characters, motions, and editing. And out of the subset is only a few which really have some meaning, which have some artistic value. Okay, so that's why it's an art, because you've got so many degrees of freedom that, well, you need to sort of really work hard to design what choices you're going to make in terms of camera placement, light placement, and characters. And a nice way to actually think of this, because we are computer scientists, so we always think of a computational model, is that film is a very specific form of visual language where you could say that an image in a movie is a letter, okay? A shot, so a shot is just a continuous camera motion, it's a word. And then edits, when you've got first shot, second shot, third shot, just changing the camera angles, it makes a sentence. So it's actually a language. So in the same way, you have NLP, natural language processing techniques, well, you could imagine having NFP, natural film processing. So the idea of trying to analyze movies and try to generate movies. So this is the idea of computational cinematography, extracting knowledge from movies and using this knowledge to try to create some new movie sequences. And this has many applications, and I'll go through some of the techniques and some of the applications we are working in our research team. So, essentially, some aspects of my research. I do a lot of film analysis. Okay, this should be looping, it's not looping, doesn't really matter. Okay, it went white, I don't know why. So I do a lot of film analysis. So in the film analysis, we can actually run some computational tools to extract things such as image composition, where are the persons in the screen. We can also extract some depth information to know what is in the foreground, what is in front, what is in the middle ground, and what is in the back. And whether it's a very deep shot with a large distance from the front to the back, or a very shallow shot, if it's like a flat shot, if I'm just against the wall and the camera is shooting from this angle. So there's a lot of information we can extract, and we'll have a look at this. And then from this high-level information, well, we can exploit it to build some computational models, and we can use that like in sports event. So I'll show an example in sports event. We can use this to generate automatically some film sequences, and we can also use it to have a sort of chat GPT-like system where you would say, I want this type of camera motion, and it's going to create automatically, using some diffusion techniques, it's going to create different camera motions that correspond to the specification. Okay, so it's running again. So this is another example of our work. We're analyzing the movie sequence. So you've got the movie sequence in the top. We're extracting the pose of the character. So that's how the character is moving. And we're also extracting the motion of the camera at the same time, and go more into details of that. So why do we want to do computational analysis of movies? Why is it interesting? Well, you can take a good example, which is computer games. Computer games are more and more cinematographic today. When you play the game, well, it's using the same cinematic techniques as you would have in movies. And that's very interesting, because we are all trained to watch movies using this cinematographic language. And if the games are using them, well, then it can sort of move you into this emotional and cognitive state of games. And this is David Cage. He's the CEO of Quantic Dream, which is a French company. And he's this idea of thinking of some sort of director who would use some algorithms based on cinematic rules from Kubrick, Orson Welles, or Coppola, and see if he could extract this information from these famous movies to try to inject that directly in the computer game. Okay, so that's the intention, and that's what we're trying to do at our level. So that means, okay, let's look at a bunch of movies, try to extract information and see what we can do with it. And we had this sort of very naive approach where we would take a bunch of movies, so here are all the movies from different filmmakers, and we wanted to try to see if we could do some movie maker classification. So from one movie maker, can we actually find some common features for this movie maker? Okay, he's made 10 movies. In the 10 movies, well, maybe there is some sort of manifold of possible techniques that he's using. And what we did is we took some small chunks from the movies. We used ResNet 18. So ResNet 18 is just a network that's going to extract image features, and it's actually quite low-level image features. And then we displayed this using a TSNE representation, so it's just a compact representation here. And actually, when you look at the results, basically what it's showing is, if you look at the clusters are actually representing not the filmmakers, but the periods. Okay? Here, 1 is 1970 movies, 2 is 1980 movies, 3 is black and white movies, etc., etc. Okay, so if we apply low-level features analysis, well, essentially what you're going to extract is only the idea that the movies have been changing a bit over time in terms of image quality. Okay, color and image quality, but nothing else. Okay, we've been moving from argentic cameras to numerical cameras, and the low-level features are only detecting this, but they're not able to detect style. They're not able to detect identity of a filmmaker because it's too much low-level. Okay, so this was sort of not really working, and we showed that it's not the right way to analyze movie sequences. So what we did is that we looked at books from film theory. So there's a lot of researchers working in film theory, and they try to do some classifications on the movies. And typically, if you look, here is a scale in terms of years, and this represents the shot scale. So when you shoot an image, if you only include the head, or if you include the body and to the shoulders, or if you include the full body, this is called the shot scale. Okay, so different movies have different shot scales, and what we actually see is that there is a trend in this where the camera is getting closer and closer to people. This is because before cameras were super heavy to move, and they would place the camera and the characters would be moving around. But nowadays, cameras are light, they can be on shoulders, and the cameras are just facing close to the images. It's the same here if you look at the mean shot duration. So the shot is one continuous camera, you would cut to another continuous camera, and you're just looking at the duration of the shots. And what has been shown by these researchers is that further we go, the shorter are the shots. Okay, so this is some sort of representation of style inside movies. So the Hollywood style of movies is making shots shorter and shorter. So there are interesting exceptions. If you take the Hong Kong movie maker like Wong Kar-wai, he's got some shots which are really, really long. Okay, so there are some exceptions. That's why you've got this high distribution here. But more and more shots are very, very short, and that's an interesting indication. You can also, at the top, display a histogram of where are the heads inside the shot. Okay, so you take all the shots together, you overlay them, and you take the position of the heads, and you can actually have a distribution of where are the heads positioned inside the screen. So if you have one actor, essentially, he's located at the third of the screen. You can probably show it here. He's located here. If you've got two actors, there's one on the left and one on the right. And if you've got more, well, then it's a bit more dispersed. So there's a lot of information you can actually extract from movies, And this is more high-level information than just applying ResNet. So we draw inspiration from this to try to extract information from movies. And typically, we were looking at image layering. Image layering is the idea when you compose a shot, you would put things in the foreground, things in the middle ground, and things in the background. Okay? And that way, you as a spectator, this will guide your gaze towards what is interesting in the shot. And this can be done just by taking some raw frames. Okay, and there are some nice depth estimators which are available. So you give a frame, it's going to give you the depth information, and then from that depth information, we use some K-means classification, and the K-means classification is going to help us to identify the different layer maps. Okay, so what are the distances between the camera and the different objects in the scene? And that's a very interesting feature of composition, whether you're having a lot of background or no background, a lot of foreground or no foreground, etc., etc. We can also use some optical flow methods. So optical flow, you would take a sequence from a movie, and then you would look how the pixels are moving over the sequence. Okay, so this represents the motion of the camera or the motion of the objects inside the scene. And actually, using this optical flow, you can run some simple classification techniques. Here it's MLP, not classification, but training, so that we can extract how much the camera is moving on each axis. Okay, is it moving on the X, on the Y, on the Z, on the rotation, on the translation? So there are more evolved techniques than this. You could use structure from motion, from robotics, but structure from motion only works well when the images are super clear and crisp. But if you look at cinematography images, well, you've got motion blur, okay, and you've got depth of field effects. So large parts of the shot is not clear. I mean, it's fuzzy, okay? And you cannot detect like Harris corner points or sift features in that if you want to track properly the camera. So it's a nice way to just classify the motions to extract some high-level information. So given that, we see that low-level information is not working, we can move towards higher-level information. And we're going to see how this high-level information can actually be used for some applications. And one of the applications we've been applying this to is sports broadcasting. So sports broadcasting is obviously a very well-funded industry, so it's interesting to work in that discipline. And we've been collaborating with the Unity game company using volumetric reconstruction to capture sport performance. Okay, so this is close to real-time sport event reconstruction. So there are multiple cameras, I think 12 cameras, which are around the scene, and they are doing close to real-time reconstruction of the event. Okay, so at each frame, all the cameras are capturing a shot, and then there's a 3D reconstruction. It's a mesh-based 3D reconstruction, and it runs with a 1 second delay. The interesting point here is that once you've reconstructed this, well then you can move the camera where you want inside this environment. Okay, so you can reshoot something, or you can place the camera at a very specific angle, or you can run some slow motion, maybe if there is some sort of punch, okay, you can run some cinematic slow motions into this. So there's a real benefit here in, if we can capture sport events in a synthetic way, then we can run some cinematic effects inside these sport events. So that's what we proposed here, and our idea was, at a first stage, to try to reproduce the style of UFC, which is Ultimate Fighting Championship. Okay, so we proposed a fully automated system which extracts the events from the volumetric capture performance. Then we moved the cameras and we cut between the cameras following some of the analysis we did, and we show the analysis, and then we run the system in real time. So it's a two-stage process. First, we try to understand what is the style of cameras in this sport event, and then how we can reproduce this style in a virtual environment. So, process is the following. In the first stage, so here we have real data. So we worked with the people from UFC and Unity, where they had some real performance with some different cameras, and we had the feeds from all the cameras, as well as the final edit from the broadcasting. And this helped us to know, among all the shots, which one was selected at what time. Okay, so why did the editor select this shot, and why did he cut to that shot? So that helped us to understand what were the interesting features. And what we saw is actually that orientation of the characters is important. Okay, so the filmmaker or the cinematographer with this camera would try to favor shots where you can actually see the front of at least one of the opponents. Visibility is important. If one character is hiding the other, well, probably the shot is not very good and will never be selected. And also facial visibility. Facial visibility is something which is important above body visibility. So we run this analysis, we see it in detail, and then in a second stage, from this footage, we could build a 3D volumetric data, and from this 3D volumetric data, we would use the statistical analysis to try to understand what are the rules that were used in this environment. I'll just show how it works. So the first stage is extracting information. So you've got different cameras, and from these different cameras, well, we extracted the body and face visibility because we saw it was important, but also the distance between the players. Okay, which is quite easy to have, and also the on-screen position and the shots. So this is the different type of shots that they had, which is the cowboy shot. The cowboy shot is when the camera cuts the person at the level of the hips. This is the full shot when you see the characters in full, and this is the last shot. And we show the distribution of heads positions here in these shots. So we've got all the statistical information that we could use, and we used this information to try to better understand what was important. So I'm not going into too much details, but basically here we were looking at what are the probability density for the different features. So this is like the facial visibility. So we see the faces of the characters, and this is 0, we don't see the face, this is, we see the face, okay? And what it shows here is essentially that shots where you don't see the face of the character are never going to be selected, okay? So in blue, it's never selected, okay? While in red, it's probably going to be selected. So what it shows in red is that actually, even if you have partial visibility on the face, shots can still be selected, okay? But if you've got no visibility at all, well, sometimes it's selected, maybe because there's partial occlusion, but not that often. So we run that analysis on different features, and we came out with this sort of cost function or score value for each camera. So each camera is basically here weighted, it's a linear combination of properties, okay, and the weights were sort of hand designed from the properties. And here essentially a camera is good if it ensures the visibility and the orientation of the character for the first character, the visibility and the body orientation of the second character, and if it ensures a given distance between the characters. So this just gives us a score between for each camera, and then basically we can apply this to all the different cameras to try to know what is the best camera. So if you have 10 cameras, we have has a score for each of these cameras, and then the scores are just evolving over time, and we can decide, should we stay in this shot or should we cut to a best camera, a better camera. This is based on the idea that we have some sort of improvement factor. So maybe a shot is good, is dropping down, and then we cut to 1, which is going to be 10% better here. If this threshold is too low, what happens is that you would cut to one camera, cut back, and you would be bouncing between cameras. Too reactive. Okay, so then in terms of online computation, I'll just throw all these videos starting at the same time. Oops, sorry. So here, as we get the real-time volumetric captured data, we're going to run, so this is the reconstructed data we get. So we're going to run some skeleton pose analysis, and then we're going to replace the skeletons by some proxy geometry, because this helps us to compute the visibility. Okay, we need this information to know whether the heads are visible, whether the body is visible or not. Okay, it's very complex to run on this because this is a mesh, and the 3D mesh is very expensive. So we've got a body proxy here, and this helps us to reconstruct this in real time. So in real time, receiving the feed, we know what is the distance between the characters, we know what is the body orientation, we know head orientation, and we know the distance between the characters. So that means for all new cameras that we're going to place in this environment, we can decide what is the best camera. So it gets a bit messy when the characters are on the ground. So each camera is also going to try to maintain a composition, a shot composition that corresponds to the initial distribution. Okay, and here is one of the algorithms we implemented, which was essentially trying to keep the characters within some box constraint inside the image. So each time the character was getting outside of the box, where the camera would pan or the camera would zoom. Okay, and this is just an automated behavior we designed, which is very simple to do. And when we run the analysis, we got a similar distribution to what we had from the original shots. So just to show a result with the full system, so both how the camera is framing and then how the camera is cutting. Okay, so this is a result out of the box. You see the camera is changing angles and zooming at times, and then cutting at some moments to different angles. So even though sometimes there are some occlusions of the heads, it's very short time occlusions, so it doesn't push the camera towards a change. So then that's fully automated. We receive the stream from the 3D reconstruction, like one frame every 1/25th of a second. We run the pose analysis, and then we decide which camera is the best one, and should we cut to another camera. So just to display, we have a sort of a visualization tool for debugging. I'm showing here. So here's like 5 cameras that were placed in the environment. The color represents, blue represents a bad quality camera, and red is a good quality camera. So you see above how the area changes. So essentially, if you put the camera in the blue region, it's not going to be good because it's going to hide one of the face of one of the characters. And this is the system running, where you have the live input. You've got the 3D reconstruction here. You've got the proxy geometry, and then you've got the system which is choosing, okay, this is currently the best camera, and then it's going to cut to another camera as soon as the situation changes. So this, in a way, sort of reproduces the style of this content, of this context of a Ultimate Fighting Championship. And actually what we wanted to do is to change the number of cameras. So here we put 20 cameras, but which were completely different in the system. Okay, so these were like hand-placed cameras, and the system behaves exactly the same. Okay, so you can view new shots in this environment, and you will have the resulting edit with actually viewpoints which are not possible in the real scene, because you cannot put cameras inside the cage. Okay, you will never have cameras inside the cage, but here you can do that. So currently this is fixed cameras, but what we're looking to is to have also moving cameras inside this environment. But at least it has retained the rules and is able to reproduce the statistics from from what we learned or from what we analyzed in the initial sequences. Okay, so takeaway message on this. Well, sometimes you would say, okay, deep learning is the solution to everything. Well, actually, no. You can use simple statistical analysis from the movie sequences, and from the statistical analysis, well, you can reproduce stylistic effects. So there's more details in the paper if you want to know how we validate the results. There's obviously some interesting ways on how to improve the work, which is, well, could we add some much more cinematographic effects inside the fighting scene? So you would try to recognize, okay, this is a punch, because you know where the head is, you know where the hand is. You could recognize a punch and then run some really nice slow motion cameras on that. Okay, and that would be really interesting. We tried to do it, but the problem is it was based on frame per frame mesh reconstruction, which means that if you run in slow motion, well, in between, it's a bit undefined, okay? Because you would need to interpolate the mesh, and when you interpolate the mesh in between, the results are not that great. So we probably need some better interpolation techniques, but at least there is some potential here to show cinematographic motions. And our idea is to then take some movies that talk about box or Ultimate Fighting Championships. We have got these nice cameras motions, and then reuse these motions inside this environment. Okay, so this is nice, but it also requires me to watch a lot of MMA movies. Okay, not that interesting at all, but it's part of the game. I'm now an expert in the field. Okay, so that's nice. We saw that we could use some very simple statistical analysis to generate some shots and some edits. But what also would be nice is to see if we can draw inspiration from some famous movie shots. Okay, so there are some very famous movie shots, and from these movie shots, well, can we try to transfer the style of these shots to a 3D environment? And that's a work that is called the JAWS, which is a cinematic transfer. So this is an example. Sorry for the low quality, it's a GIF, but there are some other ones. So you would have on the right an original sequence from a movie, and then you would want to try to transfer this motion. You really like the way it's framed, and you like the way the camera moves, and you want to transfer this motion to a 3D scene. So actually this is a 3D scene. Well, it's a 3D scene, but using neural radiance field reconstruction. So I don't know if everyone is aware of it. So this is a 3D reconstructed scene using radiance field. The idea of radiance field is that if you have a collection of images, okay, so you put like 30, 50, 100 cameras inside the 3D scene, and if you have inside a real environment, you have all these cameras, then you can try here, I'll use this, you can try for each point inside the scene, you can try to reconstruct a radiance function. And this radiance function is going to give you the color of this point here, given the viewing angle, okay? And here, each of this point is going to be learned through a small MLP. Okay, so this small MLP is basically what is the color of this point if I look through this camera, what is the color of that point if I look through this camera. So what we're learning for each point of the scene is how much light is it emitting in each direction. Okay, and the process is basically, since we know the final images, well, we can regress what are the parameters of each point. And this helps us okay, it doesn't want to turn, okay. And this helps with a collection of probably 30 or 40 photos. You can actually reconstruct a scene. And this is what is done here. You've got this real environment, and with the neural radiance field, you can capture a synthetic representation of this, which is super realistic. It's super realistic because it can handle interesting light interactions, such as specular effects. So it's not reconstructing a scene using 3D meshes, but using a neural representation. This is our objective, and how do we do it? Well, a nice way is to say, okay, this is what we want, this is what we have, and what we're going to do is to just try to compute the differences between both sequences. And if we can compute the differences, well, then we can probably try to back propagate towards the camera to say, okay, given this loss function or this difference, we can try to decide how should we move the cameras so that we're going to minimize this loss. And what's really interesting is that if we're using a neural radiance field, well, it's a method which is differentiable, okay? So, given the rendering here, we can actually back propagate through the rendering process to decide how are we going to move the cameras to minimize the loss between the two images. So what we did is, if we want to reproduce this sequence, there are multiple cinematic effects which are interesting. First is probably where are the characters in the shot, okay? You want to put the characters at the same position. And this is easy, so we just use some skeleton analysis, and with the skeleton analysis we can deduce some like temperature fields here, basically knowing these are the different joints, and we can use these different joints to compute the loss between the two shots. So here we've got the original shot, here we've got the radiance field shot. We compute these heat maps, and from these heat maps, well, we can just compute the distance function. And here we're using specifically a Wasserstein distance, which offers a better convergence of the system. So, if we want the shots to be similar, we should have characters at the same place. And we also should have the same sort of motion in both of the shots. And this motion, we saw it in the beginning, that can be extracted using optical flow. Okay, so optical flow is how the pixels are moving inside the image. So why not just extract optical flow from a short sequence of the synthetic environment, extract the optical flow from a short sequence of the real environment, and then measure the difference between them. And this gives us the loss that is then going to be used to define or to constrain how the camera is going to move in this environment. So if you go back to the pipeline, we have here the reference views. Okay, so this is the original shot. We have the synthetic views. We have a given camera here, okay, which is the original camera we give, we place initially. We render the scene using a neural renderer, okay? And then we're going to run both the pose estimator and the flow estimator at the same time on both the reference and the rendered views. We compute the differences here. Then we're just using a guidance map because actually there is a lot of data both in the heat maps and in the optical flow, so we used some sort of importance sampling to reduce the amount of data, otherwise the back propagation was too expensive. So this is just a guidance map to help us select interesting features in the image. And then, well, we can back propagate this. So we're trying to minimize the difference in flow and in heat maps so that here the sequence are going to look the same. And the parameters we're going to play with is essentially translation, rotation of the camera, but also speed of the camera. Okay, the camera can move fast or can move slow in this environment. Okay, so some iconic shots. You probably know this shot from the movie Jaws. Okay, given the name of the paper here. So you can see it's on this neural-based reconstruction scene. So there are some artifacts if the camera gets too close, because this is a very deep shot and this is a shallow shot. So the transfer is not ideal. It works a bit better here, where you can see how the deformation happens in the background. So in a nice way, you give this as an input, and then you can apply it to any neural region scene that is reconstructed. Okay, other examples. Here at the top, you've got what we call a crash zoom. Okay, so this is the camera moving very fast to the content. This is a handheld camera. Okay, it's over the shoulder, so you see there are some motions, small motions inside, and then transfers, and you will see the scene moving a bit in the same way. So it keeps the composition of the shot. So where is the character on the scene? So you would see here it's at the same location, and it's also keeping the motion of the camera. So it's a nice way to perform this transfer. And this is another example. Here we have the input shot, and here we have the resulting shot. It's also using a neural radiance, and this was like 2 years ago. It was the first examples of neural radiance for an animated scene, which is now has gone much better, and people are using Gaussian-backed representations, which is another neural radiance encoding. Okay, we can also use it to animate cameras in 3D environments. So this is the reference clip. You can see here the optical flow of this sequence and the way it's actually going to reproduce the motion of the camera in this specific scene, which is interesting for filmmakers or 3D storyboarders, because they can say, okay, I've got this sequence of characters. I like this shot, I will drop it, it's going to run, and then if it's okay, he keeps it, if it's not okay, he selects another one. So it's a nice iterative process. Okay, so what we show here is that we can easily capture some high-level cinematic features, such as composition and optical flow, and we can transfer them what would be nice also is to actually see if we can take a real movie and try to re-cinematography it. So I don't know there's some sort of artistic value to it, but re-cinematography would be the idea of you have this famous shot and maybe you want to change the camera angles, or maybe you want to change the lights, or you want to change the background. Discussing with people in the VFX industry, sometimes they shoot a scene, but they want to change something afterwards. And that's very complex to do. But there could be a potential in these approaches to try to, from different cameras, capture actually more than only from one camera. You would capture from 10 cameras, so you had a full neural reconstruction of the scene, and then you could reshoot as you want inside this environment, like changing the depth of field, changing the lights, changing everything. And that's a very interesting way to think of it in the VFX industry. Okay, last, we've been talking a lot about how we can extract knowledge from sequences at the level of a shot. And what we did in this work is to try to extend the approach by better understanding the correlation between the character's motion and the camera's motion. So the sort of behavior of a camera, how the camera is going to move in relation to how the characters move. Here what we did actually is to work on a diffusion technique that was trained on a large data set of camera motions extracted from real movies. So we provide here this very large data set. We'll see. We've both extracted how the characters are moving and how the cameras are moving. Okay, and this helps us to understand what is the correlation between both. What is the amount of motion of the camera when this character is going to move. So from this data set, we run a diffusion technique. So the diffusion technique is just to generate automatically the character and the camera motions. And we also use some constructive techniques, constructive language trajectory techniques. I'll show it just afterwards. And this stems from a first paper we had, which was a sort of a ChatGPT, but trained on synthetic data. This ChatGPT would say, okay, the camera pushes into the character, the camera moves at front, and it will generate automatically these types of shots. And it's interesting because we gave it to artists from a CG company, and the first feedback was, I don't need it, I can make trajectories by myself. It's my job. But then when you give it to them and they play with it, they get interested, okay? Because they can try hundreds of possibilities in a very short period of time. And that's one of the key of creativity, is that, well, if you can iterate very quickly, you can test and validate, well, then you can easily create something which is new. Okay, so this is the prior work at Eurographics. It was a diffusion based. So essentially we had a script description, okay, which was encoded into a clip embedding, and then we used diffusion strategy, which is only diffusing camera trajectories. So given objects, we're going to create through iterative stages the different trajectories. It was nice, but it was based on a synthetic data set. So we built by hand a bunch of camera motions, and this was laborious and probably doesn't represent real life. So what we wanted is to move this towards a real data set. And that's what we did up here. So this is the sequel of the work, where we ran some analysis on some real film sequences. We extracted both the body pose and the camera pose. And this works with a regression system, okay? So it's an optimization system where you're estimating at the same time the pose of the body and the camera, and when you reproject the pose on the camera, you're going to check if it corresponds to the original sequence. Okay, so it's an optimization process that is just going to regress both the parameters of the character and of the camera at the same time. And then what we did is that we decomposed here the motion of the character and the motion of the camera so that we could have a description of it, a textual description of it. I'll go through the details. So we provided this very large data set, very large data set, so there's 120 hours of movie sequences. Here there's 115,000 samples, more than 11 million frames. And at the time, this was 2024, it's the only data set that was run on movies. And it's now being reused by other people who are trying to do some more movie analysis. So once we had that data set, and this is how it was produced, so we run this joint optimization process to extract characters and cameras. We just did some simple analysis, okay? So how is the camera moving? Okay, so this is like a geometric analysis. It's moving in a line, it's moving in a circle, it's moving up, it's moving down, it's moving left, it's moving right. Same for the characters. And then here we run some LLM to process this caption, okay? And to give a high-level description. Why did we want this high-level description? Because then we can correlate this description with that motion, okay? And once we have this correlation, we can learn from this correlation, and then we can give a new description, and it's going to be able to generate a new sequence. Okay, so I'm not going through the details, but we use some diffusion techniques with three different types of configuration. So essentially here, this is the diffusion stage where you want to generate the camera trajectory here. And this is different types of conditioning techniques. So how you would input the character trajectory in the system as well as the description. So you would give the motion of a character, you would give a caption, and then it's going to generate the camera sequence. So we have three different constructions. So here is a traditional conditioning process, similar to in painting. Here we use the ADA-LN, which is injecting the information at different layers of the process. And finally, we use some cross-attention technique to try to make the system understand what's the correlation between the character trajectory and the camera trajectory. Okay, and also we designed, so in the same way you would have CLIP, which is contrastive learning for images and descriptions. We designed a new metric which is going to relate trajectories with descriptions. Okay, so it's going to train on a large data set and give you what is the most, it's going to give you a feature space actually where you correlate the descriptions from the motions. Which is nice because when you're going to generate some new motions from a description, you're going to see whether they are within this, this space or not. Okay, I'll just skip the analysis, but essentially the best configuration was the configuration C, where we used some attention to condition the system. Okay, look, just some examples. So here, the camera tracks to the right while the character remains stationary. The camera tracks to the left. I'll probably just replay this one. Okay, the camera booms bottom while the character remains stationary. The camera booms top while the character remains stationary. It's exactly the same text input for the person, and then we can just change the way the camera is moving. Also, if we say, okay, while the camera moves right, the camera performs a boom bottom. So the boom is the camera slowly moving down. And here in this sequence, I'm just replaying it. Okay, so it's just different ways from the same prompt. There's different ways the camera is moving. Okay, and we can try to run some more complex motions of the characters and of the camera. So when the character moves to the right, the camera stays static and pushes in once the character stops. So since we have this annotation of what the character is doing at what time, well, then we can condition the camera to move and correspond to these motions. Okay, so different descriptions we have here from the sequences. These are different descriptions from the data set, and it was really interesting to see how we could try to condition the motion of the cameras from these high-level descriptions. Okay, I just want to end with a short extension to the work. Things are moving fast today, very fast. We were 2 years ago playing with the system. We were generating motions of CG cameras, but actually now you have some fantastic video generation tools. Okay, and with video generation you can actually condition the generation of the video with some information on how the camera is going to move. So it opens exciting perspectives as to what is going to be the creative tasks of tomorrow. Maybe there will be no more 3D environments. Maybe you will just have some sort of high-level textual descriptions, some regions, and you would say, okay, I want this panoramic motion, I want the character to be here, and there's no 3D tool. Well, it's just going to generate a video, and then you can edit in the video space. Because that's all the things the artists are looking for, is generating in the image space. The image space is the only thing which is important for people. And this is a work we did where the idea was video generation is of course fantastic, and when you see the quality of what is output, it's great. It captures even very precisely light effects, which is amazing, and small camera motions and character motions. It's getting better every day. And our idea was to try to see if we could reproduce some well-known effects related to the camera focal. So this is a zoom of the camera here. There's also distortion. So you see how distorted cameras, they have effects on the image. And this is not really being done in video generation. Video generation, you would just generate a video, but you have very little control on the lens, how the camera is acting. You see this is in focus, this is out of focus. And this level of control was not available yet. Okay, so we proposed a system. I'm not going through the details, I'll just show some results, but essentially we used an existing video generation tool. Okay, so you would give a description as an input, you would give a noise because it's a diffusion process, and it would generate a video. And we run some augmentation on it so that we could actually play with the focal length, play with the lens distortion, and play with the aperture. The aperture is what is in focus and what is out of focus. So what we did is that we had a collection of frames. Here, through the actual augmentation process, we actually created an extended data set with changes of focal length, changes of camera distortion, and aperture. And then we gave this as a way to condition the video generation. So we retrained not the video generation backbone, but this camera adapter as a condition to generate frames that would correspond to, I want to change the focal length, or I want to change another parameter of the system. Okay, so just going through some few results. So this is easy because it's just how the camera is moving. So it's the extrinsic parameters of the camera. So this is our approach, and these are other approaches. So you give this as a reference, and then it's going to generate some videos with similar motions. What is more interesting here, also here it's still on the camera motion, so you see how from this reference we are able to extract the motion and then generate a new video which corresponds to the same motion, and it gives a result which is in a way similar to other approaches which exist, such as camera control. But then we went further and we played with distortion. Okay, so you can see here how there is distortion which is applied here, how you can play with zooming in a very coherent way, and more importantly is how you can play with depth of field effects. Okay, so here you would give a clip description. Okay, this is a chessboard, and then you can specify how you want the depth of field to be, if it's a very shallow depth of field or a very flat depth of field. Same here, you can even play on the focus point. So the focus point is what is the area inside the image which is in focus or out of focus. Okay, so you see in this sunflower, starting from here, the focus is there, and then the focus is slowly moving. So everything you could do in a CG environment, now you can do it with a video, which is very interesting. Okay, and this is a reproduction of famous vertigo effects, where you give the reference clip, okay, and then you can create the same sequence. Okay, so this is super interesting because this is a time where we're transitioning from 3D representations to directly generating videos. We've got powerful tools to now do some precise control on camera lenses, and we can achieve some well-established cinematic effects directly inside the video. Is this the future of media content generation? Maybe, in some way. It's quite an open question. Okay, so just to conclude quickly, what we've been doing together is trying to understand cinematic style and cinematic effects from movies in a statistical way, either using learning techniques or simple statistical way. But actually, what we're missing is the meaning, because a filmmaker, when he wants to create a sequence, he puts some meaning in it. Okay, I want this sequence to have a specific meaning, and when we do our analysis, we don't have this meaning part. Okay, we don't know what is the meaning of the sequence that we generate, and this meaning actually comes from the filmmaker's intention. The filmmaker, when he creates a sequence, is going to say, okay, my intention is to put the spectator in a cognitive and emotional state. Okay, but we don't have these intentions. We don't have the intentions, we don't have the meaning, we only have the output, we have the result. And that's probably not enough. And there's a good illustration of this, which is an experiment done by a Russian filmmaker, which is called Kuleshov in 1923. This is the first shot, this is the second shot. And the meaning of this sequence is completely different from the meaning of that sequence. Because what happens is in between, okay? When you cut from one shot to another, it's going to give some meaning to a sequence. So here, he's probably thinking about eating, here he's thinking about his family. Okay, but the same first shot is exactly the same. So, if we don't understand how this is done, well, it's going to be very difficult to generate automatically some cinematic sequences that have a meaning. And there is this very interesting definition of storytelling. It's the art of bringing an audience from a given cognitive and emotional state through a set of cognitive and emotional states. Okay, if you watch a movie, they're going to bring you to be happy, to be sad, to laugh, and to cry. This is very interesting, and if we can try to better understand how this is done, then probably we can create some better sequences. Okay, so thanks, and these are the collaborators with whom I've been working with, and I'm happy to answer any question.
Any questions?
Hi.
This works.
Hello, thank you. I'm very interested about the draw, the paper you mentioned, like the style. Is the original input a picture or a video?
Which work?
The draw, like
JAWS, yeah. So, sorry. This one.
A few previous slides, like yeah.
Okay.
Is the original input an image or a video?
It's a video.
Okay.
Yeah. So we take this as an input video. Sorry. Come on. We take this as an input video, and then we analyze where are the characters on the screen and how is the shot moving.
Okay.
So it's input. But I agree with you. You could imagine it's a drawing, like it's a sketch. If you make a sketch with some motion, then probably if you rewrite a bit the cost functions or the loss functions, well then you could probably use a drawing as an input to control the system.
So like you trained on this stuff and you get a neural network of doing this style. So you have to give the input video like if the original, like in the Matrix, they have two characters. You have
Yes.
to have two characters.
Yes.
People in that input video.
Absolutely. I mean, if you give a new 3D scene here, which has only got one character, well, the behavior of the system is sort of undefined. Okay? It's like the artist knows he has two characters, so he's going to look for sequences with two characters to try to apply them. Otherwise, it's a bit meaningless.
Okay. I was just I'm curious about if you like train it and then input it with like a scene, the same scene but without characters. What would be the
Probably the loss here is going to be very bad because you will have a heat map here but no heat maps in the second one. So this loss is going to be very bad, but the only difference is going to be made on the optical flow, and probably the optical flow may be enough for the system to converge to a similar motion of the camera.
But the character plays a critical role.
Yeah, the character, it wouldn't work because there would be no points detected here, so the distance would be very high,
Okay.
and the loss function would be not relevant.
Thank you.
I would be interested in, especially so for the meeting that you also brought up, so for the UFC style video and like the shot composition, do you think that it would be more complex if you didn't choose UFC as as what you're trying to capture? Because I think in like fighting like this, obviously what the viewer wants to see is like the object that they want to track is the human body, and a lot of the metadata that you guys seem to focus on seems to be very human-centric, like the faces and the bodies, which aligns with what UFC is trying to capture, right? So for example, if you guys were to use other kind of sports for this, like football or maybe golf or something, where there's a different kind of interaction between what the human does and necessarily what the viewer is interested in, like the ball or some other kind of object. Do you think this would make like getting this kind of statistical analysis much more complex because you have different interactions at what point the viewer might be interested in a specific player as to the objective of the game itself, which is more focused on like maybe the ball that is moving around?
Yes, it's a very good question as to how transposable is this approach to other sports. It's obvious that if you take large group sports like rugby, football or whatsoever, you would be interested also in the goals, okay, the shooting cage, and in the ball. And so you would probably need to add some analysis as to what are the shots which are covering the motion of the ball and the goals at the same time. But this is just a statistical analysis, so you could run on the 20 cameras that are shooting the scene, which are the ones that are looking at those elements and at what time, at what conditions. The only thing is that probably the conditions at which you're looking at the ball and the goal are a bit specific, because maybe the player needs to be at a given distance from the goal, maybe he needs to be in a confrontation with other players, so it's probably a bit more subtle, but I believe standard statistical analysis techniques could be enough to try to discriminate that.
My other question is regarding the meaning. So when you mentioned that meaning is absent, did you try to analyze the
Need to push it to the up.
So my question is also regarding the meaning. So when you said that meaning is absent,
Yes.
or maybe we don't know, so did you try to analyze the scenes or movies from the same director? Because for example, many directors have their own styles, or maybe in particular era their styles evolve. For example, some directors try to, for example, during the fight, so some directors try to focus more on their pace. So they try to see the intentions behind the person who is fighting. So maybe there is a meaning behind that. So did you try to analyze particular style of directors, like a single director? There's movies from the single director.
Yeah. So we didn't specifically do that, but there are some people that have been looking at framing and specifically how framing evolves from one director to another. Each director has got his own signature of how you would compose the shots and how you would cut. It's true for some directors that have this signature, but you would take someone like Steven Spielberg, from one movie to another, he would have a completely different signature. Okay? Because he is known to have choosing some camera angles which other people wouldn't choose. Okay? So it's probably very difficult to say, okay, I want this movie to look like Steven Spielberg. You would probably need to be very more specific and say, okay, I want to look very specifically at this movie from this filmmaker. But there are a lot of people in the cognitive science discipline which are trying to understand movies. So there's a society called the Society for Understanding Movies. And it's a small group of people that are looking at movies and trying to really get a grasp of what is the cognitive and emotional impact of a shot, and what is the cognitive and emotional impact of a transition from one shot to another. Why is this magic happening? What's happening in our heads that makes us understand, okay, this is the good guy and this is the bad guy? And that's a very interesting basis to better understand it.
Just to add one more part, for example, when I see a rhymes or some movies, I see that there is particular style. So like in the continuing this previous version, so like when we see the faces, so we see the intent, like they want to see how the person is thinking during the fight. So don't you think that there's a pattern, like there's intention behind the characters? So
yeah, obviously there is many cinematic recipes that filmmakers are using. Like intensification. So intensification is that you're having a large shot, and then a closer shot, and then a closer shot, and then a closer shot. And obviously, you're trying to draw the attention of the spectator towards that. But you're not actually, so you can reproduce it easily, but the meaning is going to be completely different depending on what the character is performing. So you would need to have an idea of what you want the spectator to understand. And if you know what the spectator should understand, then you need to design the motion of the character, probably what the character is saying, and then how the camera is moving towards the character.
Thank you.
So, the last question, because we are running late. Okay.
Thank you. I'm curious about the work on the screen. If we replace the
Which one?
just that work before you move yours.
Okay.
When I replace the neural renderer with a traditional render pipeline, then it seems that it will be very hard to calculate the gradients in the back propagation process. So my question is about, are we able to apply some non-gradient descent-based optimization, but also achieve that work?
Yeah. That's a very good question. Well, the only issue is that non-gradient-based optimization is prone to a lot of local minima because you have no gradients or you are acting in the discrete domain, which means that it's very difficult for the system to converge. So what people are doing is that they're actually replacing a complex non-gradient based by a simple representation in which you can have gradients. So you're using a sort of proxy representation in which you can run the gradients and then hope it will converge on the real content. But I agree that nowadays people are working a lot on differentiable rendering engines, even mesh-based differentiable rendering engines. So tomorrow, I think, just from a final image, we will be able to go back actually to the source of the image, better understand what's the material, what are the properties of the material, what are the lights, what are the camera parameters, what are the lens parameters. This is going to be able to be done by some back propagation directly, because from the rendered image, from the image you capture from the real life, you will be able to do some differentiable rendering to understand, okay, well, this is plastic, this is metal, this is neon light, this is sunshine, and then you will have a better understanding of the scene. And this is differentiable, so you can do anything with it. It's a great approach.
Okay. Be honest, I didn't expect so many questions from the students. So that means that the talk is fantastic. Let's thank Professor Marc again.
Thank you. Sorry to keep you late for lunch. It's all good.